Okay. Hello, everyone, and apologize for starting late. Today I will be mostly a review session, and it should be pretty quick, hopefully. So I will review several things. It has been going pretty fast. The lectures have been going pretty fast for the past few weeks. We've been talking conjugate descent Newton methods, quasi-Newton methods, and duality KKT. So basically what I will do today is I'll briefly talk about quasi-Newton. Duality and KKT. So it will be mostly about things you've already known, but I just want to clarify, you have a clear picture of how these actually how you actually understand them. So first, I'll talk about quasi-Newton methods. So this one was motivated from quadratic programming. And for example, you have in a 2D plane, a quadratic function will have a level map that looks like something like this. For example, this is f equals to maybe 2. This is f equals to maybe 1. Okay, and you start from some node x, and you calculate this gradient maybe along this direction, but then you don't actually walk through your gradient. There's no requirement that you actually walk along the negative gradient, right? For all the Newton methods, quasi-Newton methods, you don't actually walk directly opposite to your gradient. What you do is you walk a skewed direction that is the best knowledge of your idea of this shape. So ideally, you want to walk somewhere here. In Newton method, it will be directly, because Newton method is motivated from quadratic programming. So suppose this is your gradient g, then your direction will be d equals negative Hessian inverse g, which will go directly to the center of the function. In a quasi-Newton method, you don't actually have this H inverse. So you might have some very bad guess. You might walk toward this direction. And this is your direction G. But still, your direction D. Still, you want to have a decent direction. So you want this D and G to be like on the different sides of this tangent line, right? That basically says, so suppose your D is constructed in a way, maybe your D is some S times G, then you probably want to have this D transpose G to be smaller than 0, right? What could guarantee this is if your S is a positive definite matrix, then this will be guaranteed. And how long do you want to walk? You want to walk so that the function along this line is minimized. And this particular point here, well, geometrically, you think about you're cutting. So suppose this is a shape, this shaped paper, and you have a scissor, you just cut along this line. What you'll get is something like a curve here. And the minimum will be the point where roughly the gradient is orthogonal to your direction. So one way to do is you minimize the function value x minus or plus alpha times d. The other method is, which is equivalent to the fact that your new gradient, let's say this gradient is g. Sorry, the gradient should be the other way, right? Let's say this gradient is g plus, then you have D transpose G plus, they are perpendicular, right? And you can solve for alpha, given that at any point your function, this function x is x, let's say it's a half x transpose qx minus b transpose x, then the gradient will be exactly qx minus b. So you plug this in, but here you replace g by g plus. And g plus is the gradient at the destination. So you also have g plus equals q times, what's your destination? Your destination is x plus alpha d minus b. This is your new gradient. And this part becomes your old gradient. So essentially you have alpha times qd plus your old gradient. This is only for mathematic simplification. So now your new gradient and your old gradient, you plug these in, you know your optimal step. And this is d transpose alpha qd plus g transpose d transpose g. This is 0. So now you have your optimal step size, which is d transpose qd. Right? And this works in conjugate gradient in like quasi-newton, in anything that you specify the direction and you're working in quadratic programming. And I guess you're pretty familiar with this one. Right? And what quasi-Newton method says is, maybe I should work on this, is that once you move to this new direction, your gradient also changed. And through the change of gradient, you can compute the Hessian. That's because, so suppose I'm working on a circle, okay, a sphere, and this is my gradient. My gradient is always like the radial direction. So I move to this place, and then my gradient becomes this way. So I can compute the gradient by the difference of the gradient will be along this direction. So because you can move this, you can translate this one to here, and then it will be a similar triangle to this triangle. And why do I want to mention that? Because mathematically, you have g plus minus g, which is qx plus minus b minus qx minus b. And this becomes qx plus minus x. And so that means basically in a circle, your movement and your displacement will actually reflect your change of gradient. In a I don't know, ellipsoid, your influence is actually skewed by this q. And that's the way you compute q. And then we talked about this rank 1 update, which basically says, so if I rewrite q plus minus q, g plus minus g, which is the change of gradient, if I write this one as q, and then I write this one as qp, where p is the displacement, then I should expect this equality. But I don't, because I don't have the correct form of q. Suppose now I have my estimate is, so in the first order, well, I guess it doesn't matter, but suppose my estimate is q naught p, and they are not equal. So I want to change Q0 by a rank 1 update. So some Q1 equals to Q0 plus AZZ transpose satisfies this equality for the new point. And then you can also verify that this Q1 also satisfies odd points, or odd pairs. And the way to compute Z is as follows. So it's actually pretty straightforward. If you write R equals to Q minus this quantity. So in the lecture, we were working on the inverse of Q, which is H. But here maybe, I don't know if this works, maybe we can just directly work on Q because they're basically the same thing, right? If you replace Q and P, then you move from Q to H, where H is, so maybe I should write here, if you can still see, P equals H times Q. So it's the same thing. And R is in this form. So then we want Q1 to satisfy this equation. So we want Q equals to Q0 plus AZZ transpose P. And then, so Q minus, this is Q0. Q minus Q0 P is R. So I want R to equal to A times ZZ transpose P. And this is a scalar. So basically, I want to set Z to be R. And A to be a normalizer so that A actually wants to, I want A to equal to the inverse of this part. So the scale will be 1. And then I want Z to be R because this is rank 1. And this is a number. This is a scalar number. So what I end up doing is I set Z to be Q minus Q0 P. And my A is Q minus Q0 P transpose Z. Okay. And this is rank 1 update. So for every Q0, if I see a new pair, I update, I fix Q0 to Q1. And this is rank 1 update. And rank 1 update, what's the problem for rank 1 update is it doesn't guarantee that this Q becomes positive definite if this quantity A is negative. So why would that happen? Because this is P, not Z. This is A equals to Z times P. So for some reason, this Q is not guaranteed to be positive definite. So we come up with rank 2 update. And rank 2 update is a more complicated form, which is essentially very similar to this one. So so by the way, this is in this book, which I forgot its name. I can send you afterwards. So you know the idea, right? This is rank 1 update. The whole idea is the whole idea is embedded in rank 1 update. And rank 2 update is a fixed rank 1 update so that you always get a positive definite matrix. And you don't have like singularity issues for A. This is inverse. Everyone cool with quasi-newton methods? Okay. Oh, you just that's a good point. I suppose you start with 0? If you start with 0, will it work? If Q0 is 0, then nothing changes, right? That's my guess. I didn't really notice. But in practice, what you do is you call the package BFGS, and it will do everything for you. BFGS. This has this is the names of the 4 authors. If I still have them printed somewhere. And also, there's another called DFP method. Right? The difference is in DFP method, we do rank2 update to the inverse of the Q, which is the Hessian, the inverse of Hessian. And for BFGS, we work on Q, but we use our updated Q to, again, give us back an H. That's the difference. And once you have an updated H, then there's a notational confusion, but what you want to do is to make this H to be your S. You multiply that. Because your Hessian is actually Q here in quadratic programming. Okay. So that's about quasi-Newton methods. I can find that eraser. Maybe let's work on this board. Now, the second part I want to talk about is duality. And duality is actually a very important topic in convex optimization. And so basically, the idea is you want to have, you have this function minimize Q of x subject to the constraints h of x smaller than 0 and L of x equal to 0. And you want to translate this optimization to a maximization of g times g of function uv such that u is greater than 0. I guess that's the only constraint here. And so the question is, how do we translate these problems? And the way is to construct a graph. The way is to construct a Laplacian. Laplacian is just you add some multipliers to these constraints, and you form a like one function. So this is this looks like this. You have your original primal variable, and you want to construct a u and a v such that you keep your primal variable. You multiply u to this constraint, u times h of x, and you multiply v to this constraint, v times L of x. Okay, so I was ignoring the labels. For simplicity, let's say we only have 2 constraints, one for each type. But in reality, you also have a summation here, you have a summation here. Or maybe I should write it. Okay, and so why this works? So for the primal problem, this primal problem translates to this very simple. You minimize x, and then you maximize u greater than 0 and v of this function. This is your primal problem. And the reason is, suppose your x is not feasible. So when your x is not feasible, for example, the first condition breaks. Now, that means if h of x is greater than 0, what you'll get is you can always increase u to make this L to infinity, right? When L is plus infinity, it's actually not useful to this minimization. Your objective is clearly smaller than infinity. The similar is true for L of x. If this constraint breaks, then this becomes 0. You can always tune v to either increase or decrease according to the sign of Lx. And again, you have L to be plus infinity. And it's not helpful. So then everyone is cool that this function is the same as our primal problem. So my constraints are enforced, and so I forgot to mention this. If x is actually feasible, that means all the constraints are satisfied, then h of x is smaller or equal to 0. What do you want to do? How can you maximize this term when u is greater than 0? So you want to put a positive multiplier to something that is non-positive. So the maximizer of this term will be u equals to 0, right? And also this part, when L is 0, it doesn't matter which value you take for v, this part will always be 0. So that gives us that when f is feasible, we have the problem exactly the same to this problem. This revised problem is the same as we get the same problem. Okay. So now we have this nice term. We don't have any obvious constraints. We have these two terms. The next thing we do is we swap the order, max and min. We swap the order. Let me just copy this our primal problem, which is min of x, max, u greater than 0, v doesn't matter, v is unconstrained, L, x, u, v. Okay, this is our primal problem. And it just so happens that the dual problem exactly becomes this one. And further, this part is what we call the dual objective, GUV. So I can show you that the dual problem is always greater than the primal problem. And that's because if you ignore this, let me see if I have this here. If you ignore this max, if you only look at this part, okay? Only look at this part. The primal problem is a minimization of something that's constrained. Whereas your dual problem is minimization of something that's not constrained. So right? So you have like a bigger space to explore in here than in here. You have more functions to consider in the lower line. So that means for this part, this primal objective is greater than the dual objective. And this is true for any UV here. So the max over any UV doesn't change the fact that this one is smaller than the first one. This is how you look at min max. If you swap them, then this swapping will enforce an order. And this order is revealed in this way. Everyone cool with the idea? I can also work on the other direction. If I hide this minimization, if I look at this problem and this problem, and I have a maximization, but here maximization is restricted. So this maximization doesn't work as well as this maximization. I still get this sign here. This part is greater than this part. And that's true for any x here. So in the lower line, x is picked such that the lower line x is picked as an adversary. It's hindering your maximization. In the upper line, x is not doing that. X is just a random neutral choice. It's not actually an enemy of you. So that's why this part is greater than this part. So that's the duality. And the called duality actually means the primal problem is always greater or equal to the dual problem. Okay. So for example, this example was talked about in class. Oh, here's the eraser. Nice. And this example is the example we had in class. So suppose I have this is my primal coordinate, and I have a function that looks like this. This is my f of x. And I also have a constraint that looks like this. And I have this part is 0. The y value is 0. This is y. This is x. And this function is a constraint. This function is h of x. So I want h of x to be smaller than or equal to 0. That means my feasible region is here, between these two bars. And what I'm putting in the Laplacian is, no, sorry. What I'm putting in the Lagrangian, did I always say Laplacian? What I'm putting in the Lagrangian is a positive fix of this function. So I'm adding some portion of this function to the objective function. So maybe if I add just a little bit, then it will be like this, right? The center part will drop and the side parts will increase. If I add the right amount, then I get this. If I add more amount, I get that look very similar to this h of x that actually loses f of x. Okay. And so then you look at the claim which describes a dual variable, okay? And when u is 0, you get here. And here I will write the dual, the g, this vertical bar is g of u. So I don't have linearity constraints. I only have inequality constraints. So I only have one variable to worry about. And this is g of u. G of u is the minimum of this fx plus ux, fx plus u h of x over the entire space, entire x. So if u is 0, then over the entire x, I will get about this value. This is the lowest part. And if I increase a little bit of u, I get better, I get here. And maybe the sweet spot here, I get a value that's larger than the value when u is 0. You can see, because this part rises, and before this center part drops below this bar, I can get something that's higher. And then when I increase u even more, I get this counter effect. I get the g of u will drop. And also, it should be noticed that even though this point is optimal, it's still inferior than the true optimal of f of x, because the true optimal is here. And this is higher than my dual optimal. So my primal optimal is somewhere higher than here. And this value. And that agrees with our analysis that the primal variable is always greater or equal to the dual solution. And the dual problem is to maximize G of U over U greater than 0, greater or equal to 0. Give us this dual solution. This is the duality gap. Okay. And let's look at an example. This example is a battle between Barnabas and Ryan. But it's also in Ryan's in Boyden's book, Convex Optimization. Stephen Boyd. So in this game, this is Ryan, this is Barnabas. Okay, and there's a table, and Barnabas can choose through 1 through m. Ryan can choose 1 through n. Let's call this value I, this value j. Okay, and if Barnabas chooses value I, Ryan chooses value j, then Barnabas gives Ryan Pij of dollar. And Pij could be negative. That means Barnabas receives Pij from Ryan. Okay. And so how this game works? So everyone has a fixed strategy. They can't change. The fixed strategy is randomized. So it's not everyone takes one step, but there's no such thing as a move, but really there's just one step. And suppose so everyone has to pick a probability distribution for example, for Barnabas, he has to choose that probability that Barnabas chooses a particular value. He has to fix this value to be xi. And also, Ryan has to choose, has to have a fixed strategy. But then they are fixed. How can they play? They play in this way. So when Barnabas chooses one strategy, one of them chooses a strategy first, and then the other person picks the strategy that's best against the first strategy. So, for example, if Barnabas has already chosen a strategy X, so what Ryan will do will be, so I want to maximize sum of xi, yj, pij, subject to y being a probability distribution. So that means y has to be greater than 0, and sum of y has to be 1. Yj has to be greater than 0, and sum of yj equals to 1. So that means if Barnabas works under this probability distribution and Ryan works under this probability distribution, then the outcome of the game. This is the reward for Ryan. Okay. Similarly, for Barnabas, if Ryan picks a solution, then Barnabas can pick a solution that beats Ryan, and his objective will be minimize xi, yi, yj, pij. Well, actually, it's maximizing of the negative, but it's equivalent to minimizing. Minimize the money that Barnabas loses to Ryan, or maximizing the money that Ryan gives to Barnabas. And here the constraint becomes x is greater than 0, and sum of xi equals to 0. Now if I write with slack variable, so this is really just one slide on their uncovered lecture notes. if I write this variable, so let's see. So this is for example, take this as an example. Then the optimal strategy for x x stands for Barnabas is that he picks the xi where this part has the maximum value. So if Ryan picks a strategy already, then Barnabas will just exploit Ryan's strategy. He will just pick the maximum value of this part to put all his mass on xi. So basically, the maximizer for Barnabas will be minimize this. So it will be actually to minimize P of y. This is one norm. No, maximize infinity norm, such that, well, there's no constraint because this is Barnabas' optimal strategy. And the optimal strategy for Ryan would be, I would exploit Barnabas. I would pick x transpose p, the infinity norm. I will exploit this value. And so this is Barnabas, this is Ryan. And this is equivalent to maximize of, so this is Barnabas' strategy, this is Ryan's strategy. And they both know that. So now, but for example, Ryan doesn't want to lose this game. So what Ryan wants to do is to decide before Ryan's optimal strategy, a strategy that actually makes Barnabas' strategy the worst. And that is maximization of y, where y is actually a probability distribution. That means yj is smaller than greater than 0. Sum of yj is 1. And then I want to minimize py infinity norm. And how do I write this infinity norm? I will just write a variable, a slack variable. Let me just write here a t, and subject to py I smaller than t. Right? So the same goes to Barnabas. We will pick minimum that x I is greater than 0, sum of xi equals to 1. P transpose x j smaller than t, and this is a t. And no, wait, did I make a mistake here? P transpose x j smaller than t. I don't actually want to. I want to do the other direction, right? So now this part, I can also equivalently write this as a minimum of t such that P transpose x j is smaller than t. Why do I have maximum? Oh, Oh, did I make a mistake? I actually don't actually have this maximization or minimization because it's determined. This is determined. So I don't have maximization or minimization. So I can just write here as the constraints greater than t, and I want to minimize t. No, maximize t. But t doesn't becomes greater than any of the coordinates. And here, I want to minimize t. Minimize t such that p transpose x j is smaller than t. Am I right? Okay, so this is the strategy of Barnabas, and this is the strategy of Ryan. And then the game is on. Let's see who wins. If one starts, like if Ryan starts first, he plays under this rule, and this is the money he will win. If Barnabas starts first, and this is Barnabas' strategy, and this is the amount of money that Barnabas will win. The amount of money that Barnabas will give to Ryan, the same quantity. And now the result is that whoever plays first, they have the same outcome. The reason is that they form dual problems. And they have strong duality, so their objective value is the same. So I guess it's not very hard, right? So if I compute the I don't want to spend forever on this problem, but if I just compute the Laplacian of the primal problem, the problem that Ryan started this game, then my problem will primal problem will be so I'll have x. I don't have x. I have y here. Am I causing trouble to myself? Okay, I have y here, and no, I actually want to start from the minimization because I'm more familiar with minimization. Okay, so let's start with Barnabas. This is a minimization, so everything fits right to our methods there. So I'm going to write the Laplacian for Barnabas, which is Laplacian of x. This is my variable, and I also have a variable t. My constraints are I have 1, 2, 3. I have two inequality constraints. Let me write them as uv, and my equality constraint, let me write as maybe s. Let's see what happens. Okay. So here, the objective is t. And I have my inequality, I will just write u, ui, sum of ui negative xi, plus sum of vi t minus, no, wait. So I want smaller or equal to always. I always want something to be smaller or equal to a constant. So here I'll write pjx, ptxj, and it's j time minus t. And finally, I have an equality constraint. So s times sum of xi minus 1. Okay. And we derive the dual of this problem. So the dual of the problem, so our dual variables are uvs, and should maximize over x and t, my primal problem. And I actually can save myself some trouble by not adding this u here. This u seems not very interesting. I just ignore u, and so I'll write here uvs. But really, I can equivalent do this. I can constrain x to be greater than 0 and my little t, and I only work on x, t, so I can save myself a dual variable u. So I have v and s. Is this a jump? Is this, or can you understand? I guess the key thing here is I want to swap this order. So ideally, I don't have any constraints in my Lagrangian, but I can also add something here. It doesn't really matter. Maybe let's just stick to the original form. Okay. So let's collect some terms. So here, what terms do I have about x? I have this term, and this term. So I have negative uixi plus sigma vj p transpose x j and plus s times sigma xi. This is all my terms involving x. And what are my terms involving t? I have plus t minus sigma vj times t. This is all my terms involving t. And all the other terms are the terms that will appear in the dual objective, which is terms not involving x and t. I only have minus s. Am I correct? This is my only term not involving x and t. Okay, and now I'm better off just writing them in matrix forms. So this is u transpose x plus this is vector type product of vector and sum. So this is v transpose p transpose x, because p transpose x is a common vector. And then I have s times 1 transpose x. This is all my terms involving x. I have p minus some, so I have a vector 1, number 1 minus sum of vj times t minus s. So this is all my terms involving t. So now, because I don't want this maximization to be plus infinity, so I want the coefficients for x become 0. So I want to enforce the constraint that u transpose plus v transpose p transpose plus s times 1 transpose to be 0. And I also want this part to be 0. So I want 1 equals to sum of vj. So let's look at here. Let's see what we can do about this term. Right. So for any x, I want this first term to be 0. So I have to have the coefficients to be 0. And by the construction, because u corresponds to this non-negative constraint, so u should be greater or equal to 0. V corresponds to this inequality constraint, so v has to be greater than equal to 0, and s is unconstrained. S could be anything. So so here, the simplest thing would be just getting rid of u. If I get rid of u, I'm only required that V transpose P transpose plus S times 1 transpose to be, if I move U to this side and I say this is greater than 0, then this is greater than 0, greater or equal to 0. This, or I should, this is equal to U transpose greater than 0. Okay, so I've cleared all my constraints. So what I end up doing is, maybe this part is enough for my calculation. So what the due problem of this problem becomes minimization over U greater than 0, V greater than 0, and S of this GUVS. And GUVS becomes, these first two terms become 0, then I only have a negative S. And plus something that's, in order that something doesn't go to plus infinity, I have to also have these constraints that basically these two coefficients become 0, and they actually becomes V PV plus S greater or equal to 0, and sum of Vj is 1. Okay, so if I organize this a little bit, minimize over, so I get rid of U, and basically negative S, such that P times V is greater or equal to negative S, and sum of Vj is equal to 1, and V is greater or equal to 0. Okay, and this, by coincidence, this just becomes the strategy for Rhine. So if I replace, oh, did I make a mistake here? Did someone notice that I made a mistake, a serious mistake here? Now, do you see the problem here? The problem is, I want to get the strategy for Rhine, but I don't have this maximization over here. And if we backtrack, I have this part. I believe this part is correct. I have this part. I have this part. So what's the problem here? You know, so ideally we started from Barnabas, right? We have Barnabas here, and we have Barnabas on the top, and then we have the dual objective for Barnabas, and we derive the dual objective. We have some constraints, and then we form the dual problem. And this problem should be Rhine, but except that we're missing a sign. So if we replace negative S by T and V by Y, then this becomes Rhine, but with a different direction. No idea. So I guess this is a very fundamental question, problem that I don't want you to make any mistake about this. So I was only sticking to the primal problem. I haven't swapped the order. The dual objective is minimization over x. So this is my dual objective. And I made a mistake. I thought, yeah, we're doing the dual is maximization, so I just changed this to maximization. But really, you're always sticking to minimization. You're always minimizing over x, and you're always maximizing over the dual variables. So here, what I should have done is I should minimize this term. Instead of maximizing, I should minimize. Okay, and I minimize here, and my arguments are valid because here, if this term doesn't become 0, then because my x could be anything, I could just fly off to infinity in both directions. And here I can go to infinity in both directions. So, yeah. So, I hope you don't make this mistake. And finally, my dual problem is to maximize over my dual objective. But my dual objective itself is a minimization over the Lagrangian. What does this mean? Okay, and this is max. So I get back to the strategy for Rhine. So we have what we call in class strong duality. I guess I should have started strong duality earlier. What is strong duality? Snade's conditions. When does the duality gap go to 0? No, I mean there's a condition. Isn't always true. It is not true for the problem I raised. The constraints are tight. Yeah. Snade's condition. So the yeah. Sorry?
The two variables times the constraints equal to 0.
Not really there. That's a prerequisite for the KKT condition. Strong duality is a prerequisite for KKT condition. I guess if you should. It's not a very serious thing, but really you just should know is that you actually want to have a feasible point that's interior to your feasible region. And that's Snade's condition. Once that holds, and once you have like a convex problem, then you have strong duality. So I just repeat myself. If you have a point in your feasible interior of the feasible set, that means these inequalities become strict. And also, if you are solving a convex problem, then you have 0 duality gap. You have strong duality. That means 0 duality gap. So I guess I spent too much time on this, and maybe finally I have this KKT condition, which basically comes from, I don't have my notes, but the KKT condition basically comes from swapping the signs. And when you swap the order, you actually want your x here to be the same x here. So how do you understand KKT condition? So because I said the duality is basically fundamentally just a switch of optimization directions, optimization order. So if your primal solution is the same as the dual solution, means basically if x star u star v star, so for every x star I can get a u star and v star in my primal problem. If I fix x, then my maximization over u and v should be not strict, but you might get multiple u stars and v stars, but there should be some of them. There must be one. Or suppose there is one pair. And suppose for U star and V star, you can get an X star. And let me come to my notes. So in the lecture notes, it's very just one page of proof, and it's really just one page. And one thing, like a conceptual thing, is KKT condition is not a due problem. Due problem is an optimization problem, but KKT condition is a set of equations or inequalities. It's a set of functions you want to solve. And here is an optimization problem. So by deriving KKT condition, really what you're doing is you're changing from an optimization problem into a equation solution problem. You're actually solving a set of equations. And so starting from the due optimum, which if I write as F star, then it corresponds, for example, to U star and V star. Then UI star, which VJ star, LJ star, LJX. And this is the term for G. And because from strong duality, if you supplement X by X star, you should get back Fx star. And because F star is feasible, then these two terms, X star is feasible, so this is smaller or equal to 0, and this is so this part is smaller or equal to 0, and this is 0. So UI star HI X star. And by duality, I have that my primal, my due problem, my due optimal should be smaller than the primal optimal. So it should be F X star. So, and this is duality, right? You see the logic fits, because this part is smaller than 0 for an infeasible X star. X star has to be feasible. So of course you have this line smaller or equal to this line. And what strong duality says is, now your due solution, your due optimal has to equal to this primal optimal. So this part needs to be equal. And because they are equal, you have this is called slackness complement, what's called complement slackness constraint, which is UI star HI X star equals to 0. And from here to here, strictly I should write smaller or equal to. Because this is a minimization and this is a fixed point. So for this smaller or equal to become equality, my X star has to optimize this Lagrangian. So I have this stationary condition. So this is feasibility. This is a complementary slackness. And for this line to go through, I have to have stationary condition. And this basically says my subgradient of Lagrangian has to equal to 0. And that enforces this line to go through. And finally, I have primal feasibility and dual feasibility. So I have primal feasible. So I have like all the constraints that I pose. So basically, HS star has to be smaller than 0. L of x star has to be 0, and U star has to be greater than 0. And that's all the constraints for KKT condition. So basically, it's a stationary, it's a complementary slackness, and this is the feasibility constraints. And that translates our problem from a optimization to a set of equations. Another view is from gradient descent. When you have no way to descend, then basically that is your subgradient contains 0. Oh, I should write equals to, because this is subgradient. The subgradient contains 0 and some other constraints. And this constraint basically means that you can ignore how should I put this? So if hi of x star is not tied. If some of them are not tied, then you don't have this KKT condition. Is that true? I'm not exactly sure.
You ignore the constraints that are not tied, because we can choose
Oh, you mean the constraints are not tied here?
if hi x star is non-zero, so we must choose ui to be 0.
Yeah.
So that means we, in fact, ignore
the Yeah. So from the viewpoint of subgradient, basically maybe your gradient, and then you have some constraints here, and you can actually slide on this constraint. Your gradient can work towards this direction, and this ui is the amount that adding this direction to your gradient, and you actually want let's see, your constraint becomes this part, and you actually want when you add positive amounts of this gradient to your objective to your gradient of f. First part is gradient of f, and this is the gradient of the constraint. If you add some positive part of your gradient to that, then you still want to contain 0 for some positive amount of this gradient of this constraint. So obviously this point is not optimal, because you can always go through this, slide through this line to go to like a greater value. But then, for example, I'm doing minimization, and I want to add positive amount. So maybe somewhere on the boundary I can add some positive amount of this constraints. Then that still makes my gradient to be like I still cannot make progress inside this feasible region. And that's the motivation behind deriving KKT conditions through subgradient method. And this is also why we have this complementary slackness, because for the constraints that are met, we can add positive ingredients because it's on the boundary. And for the constraints that are not met, they are not on the boundary, it actually doesn't help the subgradient. I guess that's all I have. Any questions or anything? Okay, that's all for today. Thanks for staying with me. Hi.
In the direction which does not change the HI, which is already 0. Is that what you are saying in the end?
No, HI is a function.
Yeah.
No, HI is a function, and HI equals to 0 is just a level bar of that function. A level set, yes. And subgradient of H is the direction orthogonal to that level set.
Okay.
And you want to be able to add some ingredients of that function, that constraint into your descent direction, because you are already hitting that boundary, and adding something along that boundary will not hurt, will not like